Let's talk about probability. We have previously discussed probability and went over the basics of theoretical probability, experimental probability, and just overall discussing what is probability. So let's refresh our memories by thinking and talking about that first. So you may even want to pause for a moment and just think, what do I remember about probability? What kinds of questions was I answering last time we talked about this? And then we'll go ahead and talk about it. So as a review, what is probability? Well, it is the likelihood of something happening, or how likely it is that an event will occur. How likely it is that an event will occur. And we can represent that in a number of ways, either as a fraction or as a decimal, or often as a percentage. And that's a skill that we've practiced previously as well, converting between fractions, decimals, and percentages. And so just a quick reminder as well, if we need to do a conversion, if we have the fraction, we can just divide, and we often use our calculator for that, to give us the fraction, the decimal, sorry. Once we have the decimal, we can multiply by 100, or, same thing, move the decimal 2 places to the right in order to find the percentage. And each of these is an equivalent way of expressing the probability. We also talked about theoretical and experimental probability, which I know a few people struggled with, so let's discuss that as well. So often, before we do an actual experiment, we want to find theoretical probability. And I want to be clear that a theory is not a guess. In science, a theory is an explanation of how or why something happens. And in math, when we're talking about probability, it means that we are calculating the probability based on knowledge we already have of the situation. So probability is, sort of theoretical probability is probability calculated using information or data or values we already know about our given situation. So as an example, imagine we are going to roll a die. So 1, 2, 3. And I know my die has 6 sides. And when I roll a die, I know I have an equal chance of getting any number because it's random, and there's no preference for which way the die is going to land. I keep wanting to say dice because that's what we say in everyday life, but technically, dice is multiple, more than one. A single is a die. So I might slip up and go back and forth, but we're talking about a single die here right now. So if I roll the die and I want to know what is the probability of rolling a 1, I don't have to actually roll a die. I don't have to have one physically present. I can think about it and predict. I can know, well, how many sides of the die have a 1 on them? Well, 1. How many sides total are there on the die? Well, a cube has 6 sides. So I know right away, without actually doing any work, or without actually doing any measurements, that the probability of rolling a 1 is 1 in 6. Or if I were to put that in decimal form, it's approximately 0.17. Or if I were to put that in percentage form, it is 17%. So it's not a guess. I didn't just make numbers up, but I just thought logically about the situation and I used the numbers that I had. That reminds me, I should describe the formula for probability as well. So generally, what is our formula for probability? Just in case we forget. It is our number of favorable outcomes. So how many times do I get the outcome or the event that I'm expecting over the number of possible outcomes? So how many different ways can I have an outcome? So with my die, there are 6 possible outcomes because there are 6 sides on the die. And how many are favorable outcomes? Well, I was looking for getting a value of 1. There's only one way to get a value of 1 on a die, so my probability is going to be 1 over 6. So that's great. That's theoretical. That's a calculation. But what is experimental probability then? So experimental probability is, no surprise, going to be based on results we observe during an experiment. So experimental probability is, it's still calculated, but calculated based on data collected during an experiment. And the last time we talked about probability, we didn't actually perform an experiment. We just talked about it in a general sense to understand the concepts. But today we're going to actually do an experiment. And let's take a look at an example here. Let's take a look at our die once again. So let's say I'm rolling, let's say I'm going to roll my die, and I'm once again going to try to measure this time, not predict, the probability of rolling a 1. So I'm going to have my outcomes and my frequency. And this might also look familiar because last time we discussed this, we also talked about having a tally chart, and also a related term was a frequency distribution table. So talking about how many times we got our outcomes. And here our possible outcomes are 1, 2, 3, 4, 5, 6. And let's say we rolled the die a number of times, and we rolled a 1 5 times. We rolled a 2 3 times, and 1 and 4 and 4 and 3. So this is our frequency distribution table. This is a summary of all, well, I guess it's not really a summary. Yeah, I guess it is. And it's a list of our results. It's how many times we got each different outcome. Now we can use this to record or determine our experimental probability. So remember, experimental probability is how many times did I get the result I was looking for, or the favorable outcome, over how many possible outcomes were there. Well, I was looking for the favorite outcome of rolling a 1, and we see that that happened 5 times. So let's put 5 on the top of our fraction. On the bottom, I want to know how many different experiments I performed, how many different outcomes, or how many different trials did I perform of the experiment, how many total outcomes did I have. So we can count. 5 plus 3 is 8, 9 plus 4 is 13, plus 8 is 22, plus 3 is 25. Let me double check that. 8, 9, 10, 11, 12, 8. Sorry, it's only 20. Math teachers make simple math mistakes too sometimes. And let's also convert this into decimal form. So 5 over 20 on your calculator gives 0.25, or as a percentage, that is equal to 25%. Also notice that's different than what we predicted. Our experiment, our theoretical probability was 17%, but now our experimental probability is 25%. Does that mean that we made a mistake when we calculated our theoretical probability? Or does that mean we made a mistake when I took measurements and found my experimental probability? No, it's not unusual for these two numbers to be different when I perform a low number of trials. I only rolled the die 20 times. I mean, that still takes a couple minutes, but ultimately that's not very many rolls in order to get a feel for the theoretical probability. So it's okay that they're different. That's just due to statistical fluctuation, and those are just the random everyday variables that affect the outcome of experiments and our event. So what could we do in order to help our experimental probability approach our theoretical probability? Hopefully you remember from last time. What we can do is we can perform more trials. So what if instead of rolling the die 20 times, I rolled it 100 times, or 200 times, or 1,000 times, or 10,000 times? As I did that, I would expect my experimental probability to approach my theoretical probability. It's not guaranteed. There is a chance, maybe some crazy freak miracle happens and I roll a 1 every single time, and my experimental probability of rolling a 1 is 100%. It is very unlikely, but it is possible. That's part of the wonder of life. You never know for sure what's going to happen. So it's not a guarantee, but generally speaking, the more trials we perform, the closer our experimental probability gets to our theoretical probability. This is basically as far as we got last time in our discussion of probability, and so I'd like to extend it a little bit now and talk about probability distributions. And so we've kind of touched on this already. We saw in our previous experiment that we have a frequency distribution table, and that shows the distribution of possible results. So let's actually focus on that a little bit more. So I'm going to rewrite that. So if we think about our experiment involving the die, I can summarize the results with my frequency distribution table. So I have my outcome, what were the possible values I could get, and what was my frequency. So let's copy those values down briefly. So my possible outcomes, there's only 6, so they're not too hard to list. 4, 5, 6. And we record the frequency, how often each outcome occurred. So 5, 3, 1, 4, 4, 3. So I can represent this with a chart, and this tells us something. We can pretty quickly see, okay, the 5 was the most likely outcome, the 1 was the lowest outcome, and I could separately calculate the experimental probability for each possible outcome of rolling a 1 or a 2 or a 3 and so on, just like I did up here. But I can also represent this as a graph if I wanted to. So let's take a look at what that would look like for a moment. So I'm going to have frequency on my y-axis. And maybe you can think for a moment and try to predict what kind of graph I'm going to use to represent this situation. And I'll list my outcomes on the bottom. Basically, in terms of outcomes, we define our random variable x as the number displayed on the dice. So the number displayed on the dice is going to be the die 1, 2, 3, 4, 5, or 6. Those are our possible values for x, our possible values for the number that appears on the die. And so those are the numbers we're going to put on the bottom here. So 1, 2, 3, 4, 5, and 6. And in order to scale our y-axis, we can look. What is the range of numbers we are dealing with here? Well, our highest number is 5. Our lowest number is 1. So we'll make sure our y-axis goes up to at least 5. I usually add an extra number just so there's some breathing room as we sketch. So I'm going to go up to 6 and 3 and 1, 2, 4, 5. 1, 2, 3, 4, 5. All right, and let's make a bar chart or a column graph in order to present our results graphically. So how many times did I roll a 1? I rolled a 1 5 times. I rolled a 2 3 times. I rolled a 3 1 time. I rolled a 4 4 times. I rolled a 5 4 times. And I rolled a 6 3 times. And so now we also have a visual representation of our frequency distribution. And if we were to plot, we could also plot this in terms of our theoretical probability as well. So let's think about that and see what that looks like. So once again, just dealing with our single die. We'll stick with the same example to keep life simple. Outcome. And instead of frequency, let's take a look at the probability. Once again, we have the same outcomes. Well, it can roll a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And remember, we found our experimental probability earlier, and we said the probability of rolling a 1 was 1 out of 6. And the probability of rolling a 2 is also going to be 1 out of 6. And the probability of rolling a 3 is also going to be 1 out of 6 because each outcome is equally likely. So the probability of rolling that 1 was 1 out of 6, or approximately 17%, and 1 out of 6, 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 and 1 out of 6. So when I draw my frequency distribution graph, it looks pretty similar to start. So outcomes along the bottom. Actually, we'll represent it in terms of probability this time. So 1, 2, 3, 4, 5, 6. And probability is some percentage. Let's say we go up to 25%. Basically, each bar on our graph is going to have the same height because each outcome is equally likely. And so looking at our graph can quickly tell us things about the distribution of probabilities or the situation we're dealing with. So when all our bars are the same height as they are here, I know each outcome is equally likely. Or if I'm looking at my distribution graph and it looks like this, and I see some bars are much higher than others, I know, okay, that outcome or those outcomes are going to be the most likely. They're going to happen the most frequency or have the highest probability. Whereas the lowest bars are going to be the least likely or have the lowest probability of occurring. So we don't have to do a lot of work with this. We just want to be familiar with the concept of probability and frequency distribution, describing it using a chart and describing it using a graph. Oops. I'm going to end this video here, and in the next video, we'll take a look at actually performing an experiment and comparing our theoretical and experimental probability for that experiment.